What's going on, everybody? It's Mr. Gustin. I am back in the physics classroom. Today we're talking about circular motion. We're going to do a couple FBDs with circular motion, kind of tracking how the forces hold things in their circular path. And then we'll also go ahead and do some math. So we'll look on some graphing standard and some math standard here just to get us more familiar with how to draw these FBDs and how they should look. In terms of circular motion, there's not much different than typical linear motion, but we'll look at those. And then we'll also go ahead and use our new centripetal force equation to help solve some F net and some force-related questions. So here we go. First thing we're going to do, I've got a person on a gravitron. As our first question. Okay, so let's look at question number one. Example number one. I've got a person. That person, I guess their arms probably not there. They're kind of standing more like this, standing like this. Arms are like this. They're riding a ride that is moving in a circle like this, and they are pressed into the wall. We call it the gravitron. It's an old ride from carnivals, okay? But essentially, it spins really, really, really fast, and there is no floor. The person is just suspended because they're pressed into the gravitron itself, and then as it slows down, the floor raises back up, and you put your feet back on the ground. So let's track some forces, shall we? There's always a weight force. We're on Earth. It points down towards the middle of the planet, always. Yesterday, tomorrow, next week, it will always do that. Because of gravity pulling us down, there's got to be something holding us up instead of falling down. The only thing acting on us on the gravitron is the wall, so there must be some amount of friction force, and it's going to be static. Better be static, otherwise it's a really scary gravitron holding us in place. If these things are going to hold me stable, those two forces had better be equal, so I'll tack on my congruency marks. If there is a force of friction, it's the result of a normal force. So if I think about the force that is holding me in the circle, there's a normal force pointed towards the center of my circle, and that's the center of my circle, making some kind of giant circular path. This is my FBD. There is a gravity force pulling me down, as always. There better be an upward force on me, that's static friction. And if there's friction, it's always the result of a normal force, because we know that friction is equal to the coefficient of friction times the normal force between those two surfaces. That's our equation for friction. So we know that to be true. Now we can see it graphically. There's a normal force. Normal force is acting as my centripetal force here. It's the force that's always going to be pressing behind my back, pointing me towards the center of the circle. These are the forces acting on me. So if I go ahead and think, what would my centripetal force equation be? Well, it's always equal to mv squared over r, but in this case, it's also equal to my normal force. I could get even crazier with this if I wanted to, because I know how normal force relates to static friction. I could even start substituting in my friction and coefficients into this thing to go ahead and try maybe find something about friction or gravity, who knows what. But this is my F net equation, my FC for this problem. Let's try another one. I've got a second example. What about going over a circular hill on a roller coaster? Here's a circular hill. There's the middle. I'm in a car that's taking me over the top of this circular roller coaster. If I think about this, I'm on top of the road or the track, but I'm still on the planet Earth. So there's FG pointed downwards towards the middle of the Earth, yesterday, tomorrow, and next week. If I'm on a surface, though, I had better also see a normal force. Now, it's important to remember and to model that this normal force has to be smaller than gravity if I'm going to be staying in this circle. If I'm in contact with the road, I had better see a normal force. This is just going at a normal speed. Over the hill, FG is downward, FN is outward at some normal speed. This is my FBD. My net force equation is always equal to M times V squared over R, which is equal to FG, which is the radially inward pointing force, minus any radially outward pointing forces. In this case, it would be Fn. Again, this is any in particular fancy speed that we're going, like nothing special about it. However, if I take this to a little bit of an extreme and I say, what is the maximum speed I can be going and still hold myself on this road? Okay? The maximum speed I can be going and still make it over this hill safely without launching myself off. What I have to think about is the faster and faster that I go over this hill, the smaller and smaller and smaller and smaller my normal force gets until it becomes zero. If I'm going to go as fast as I can just before leaving the road, my normal force will become zero. So when I think about moving at my maximum speed over this hill, FC, which is equal to mv squared over r, is going to be equal to only fg. Fn is essentially zero. When I go over this hill, I want you to try at home and imagine what would that feel like in my stomach if I go over that hill going so fast. I will feel myself almost leave, that lurch in my stomach. I will almost be leaving the road. I can feel that. My normal force is zero, as we've called it before. My apparent weight is zero. I feel weightless. That's why roller coasters take us at a maximum speed over these hills, because it's like, ooh, that's that feeling in my gut. Apparent weight is zero. At maximum speeds, this will be my FBD. The normal force will essentially disappear. Okay? Let's look more at these extreme cases, at apparent weights and at minimum and maximum speeds. So let's go ahead and do a practice problem. I've got a practice problem about Joe physics and his bucket of water. Let's do it. So it says here in my practice problem, I've got Joe physics. I'm going to actually slide you this way with me, okay? So I've got Joe physics swings a 0.5 kilogram bucket of water vertically at a radius of 0.85 meters. He makes 5 revolutions in 6 seconds. I have 2 questions for you. Question 1. A, what is the apparent weight at the top and bottom? Question 2, what is the minimum speed the bucket can move without spilling water? You go ahead at home right now and draw the FBD if you want to, okay? You go ahead, and if you want to solve this on your own, pause it here, go solve it, come check back later for the answers. Otherwise, we're going to solve this thing here together in class. This is our problem, all right? Let's start by drawing our FBD. Okay, here's what I got. I got Joe bucket. I need top and bottom. So we're going to start with A over here. A at the top. Here is my circle. There is my bucket. or water. His arm is attached to that there. But we're not concerned about the bucket necessarily. We're more concerned of the weight of the water. So we're going to look at the weight of the water. Okay? So are the forces acting on the water at the very top? I have Fg pulling on the water downward. And I also have a normal force from the bottom of the bucket acting on the water. Both of those are pressing inward on my water. Both of those are centripetal forces acting on my water. Fg plus Fn. At the bottom of my circle, this may look a little different. Fg is still pointed downward, but the Fn of the acting on the water is pointed inward, and Fn had better be larger than Fg because it needs to be my inward force. So my Fc always equal to mv squared over r is equal to Fn, my radially inward force, minus Fg, my radially outward force. Now, I sit here, I look at this problem, and I say, okay, I know the mass of the water, I know the radius the water swings at. I need to know v squared in order to find anything out about apparent weight. Apparent weight, as we discussed earlier, is the normal force. So I'm trying to find normal force. I know gravity because it's mg. I've got that down. So I need to figure out what this v value is, what v squared is. And so I must use my other data. I must use this revolutions per second type of thing to find my period. So let's do that. Let's go ahead and find what speed is. If I remember, tangential speed is equal to the circumference divided by the period of that circle. So in this case, what I have, I see the period being equal to the number of seconds per revolution. And I get 6 seconds in 5 revolutions, which means I end up with 1.2 seconds for every 1 revolution. That's my period. I'll take that. I will plug that in over here, where 2 pi times my radius, which is 0.85 meters, divided by my 1.2 seconds, this will tell me what my speed is. And my speed ends up being 2.89 meters per second in this circle. So with this value, I can now start solving my centripetal force equations. Okay? So here's what I got. I've got, let's start with the top. I like the top better. Let's just start plugging some numbers in, okay? For my mass is 0.85. My mass is 0.5 kilograms. My speed, which is what I just solved for, 2.89 meters per second. I have to square that value over my radius, which is 0.85 meters. This is my centripetal force. This is what it is equal to. Now, I need to say also mg for Fg, 0.5 kilograms, 9.8 meters per second squared, plus Fn. I only have one variable. That variable is normal force. It is my apparent weight. I algebraify. I trust you can solve this algebra. When I solve this algebra, what I end up with is that the normal force equals 6.75 newtons. This is what I get for the apparent weight at the top of the circle. Okay? When I go ahead and do the bottom of this circle, I will go ahead and plug in the same variables, do the exact same thing, but this time Fn and Fg are pointed in opposite directions. Hang on, folks, I'm looking at something here. I made a mistake. It didn't make sense in my head. Let's change this. This number is not 2.89. I got confused. I was reading my work backwards. This is 4.45. That number did not make sense when I got it out. This number is 4.45. Make sure we change that, okay? Make sure we change that. All right, back to business. Here we go. Over here, I'm going to plug this guy in over here because I have space over here. So, same thing, 0.5. It should be very similar in terms of my centripetal force, 4.5 meters per second. I'm squaring that divided by the same radius, 0.85 equals Fn minus mg, 0.5, 9.8. It's essentially, it's the same numbers, but we get a different answer because the forces are pointed in different directions. I end up with my normal force or apparent weight over here being 16.55 newtons. You mean to tell me this bucket of water feels heavier at the bottom than at the top? Yeah, it does. It does. It does. And if you want to test me on that, pause the video, fill up a bucket of water, go outside, don't do it inside, and spin that bucket around. You will feel that bucket almost like get weightless near the top and then whoom, get really fast near the bottom. So go swing that bucket, go feel it. I promise you, it will feel heavier at the bottom than it does at the top. Okay? That's question A. Question B asks for the minimum speed. So now we're going to get into a special case. We're going to get into a special case where the minimum speed at the top. So we're going to examine the top way more closely than we have before, okay? At the very top, this water is going to do something. If I'm trying to figure out what is the minimum speed, not maximum speed, the minimum speed this bucket needs to go in order for the water to continue moving on my circular path, I'm going to need a different FBD, okay? If this water is going to leave the circular path, it's going to happen because I'm up here and the water is going to fall straight down. I don't want that to happen. I want it to stay in the bucket, which means I want it to stay basically in contact with the bucket or the bottom of the bucket, but just barely. That means my normal force is getting smaller and smaller. The contact between the water and the bucket is getting smaller and smaller and smaller and smaller. And I want to find the exact point when that bucket and water almost don't touch. That means the only force acting on the bucket, on the water up here is Fg. The apparent weight or normal force has gone to 0. When I'm thinking about the minimum speed, my centripetal force is only Fg. It is only Fg. The normal force has basically gone to 0. If I go ahead and solve this, it is the same centripetal force as before. It's a 0.5 kilogram mass of water. The speed is still 4.45. I'm sorry. I'm trying to find that speed now. I'm trying to find at what speed is gravity enough force to keep it in that circle. The radius has remained the same, 0.85 meters. And the force that is trying to keep this thing in the circle is gravity, 0.5 kilograms times 9.8 meters per second squared. This is what I'm trying to use to keep it in a circle. Gravity's doing its best. Is gravity going to be enough force to do it, to keep it there, or is it going too slow? This is what we're trying to find. What speed allows gravity to be enough force? That's the solution here. I've got all my numbers. I've got V. Don't forget it's squared. This is the number that I wrote down earlier that I shouldn't have written down yet. When I do my algebra, I find that the minimum speed required is 2.89 meters per second. That is the minimum speed, or that is the speed that gravity will allow this thing to move through the circular path and still barely maintain contact with the bucket. Okay, I've worked through 2, actually 3, kind of 3.5 or 4 different FBDs, or graphical representations of these forces. I've worked through 3 different net force equations, plugged in values, and solved for things with them. I hope this is good practice. I hope this prepares you for more practice and for assessments. If you've got questions, you can drop in the comments or ask me in class, all right? Until next time, see ya!